simply a combination of kinetic and potential energy. Okay? And we usually give this the symbol E. So this is the mechanical energy. And it's going to be simply defined as the sum of two different types of energies that we now know something about, namely potential plus kinetic energy. So that's our definition of mechanical energy. So, claim is, in systems that have defined boundaries and no external forces acting on them, this is conserved. It is constant. Okay? So a pretty straightforward principle. So I can write this as changes in potential energy plus changes in kinetic energy equals 0. Another way of writing it. Many ways of writing the same thing. But it simply means if I add up potential and kinetic energies in some defined system, no external forces, this is going to be true. So it's actually very useful. And let's see, we have 10 minutes. Let's see how far I can get with this. Maybe time to do a quick example. All right. What sort of scenarios may this help us solve problems in? So, let's go back to cases that we already know. We have the tools already to kind of work with and solve problems for. Maybe motion under the force of gravity. So, okay. Throwing a ball upwards. Once it's released from my hand, the only force it experiences, if we neglect drag force from the air, the only force it experiences once it's left my hand is the acceleration due to gravity downwards. Near Earth approximation, we claim that force is about constant. We're going to talk more in detail about gravitation at larger scales in maybe a couple of weeks. So I've got a constant force, that means it's constant acceleration motion. I can use my equations of constant acceleration motion to figure out everything about this. So in that sense, why do I need energy conservation? I don't. But it provides an alternative framework to figure out details about this motion. So let me just quickly summarize how I would look at this now from an energy perspective rather than from a force perspective. So again, once this thing is released from my hand, just think about its mechanical energy constituents. So think about its kinetic energy and its potential energy everywhere along its path. So what can you tell me about the kinetic and potential energy at the launch point? What can you tell me as it goes up? What can you tell me about it at its highest point? What can you tell me as it drops back down again? From an energy perspective, let's go there.
Kinetic energy is at its highest at the launch point where it turns, and potential energy is at its max, and kinetic energy is 0 when it's at its very peak.
Okay. All right, so let me paraphrase that. It's all correct. At launch, I'm going to choose this maybe as my reference point for vertical position, maybe my reference point therefore for potential energy. At launch point, this has the maximum speed, so it has maximum kinetic energy. As it goes up, the kinetic energy is decreasing, the thing is slowing down. At that instant where it reaches the top of its trajectory, instantaneously as it rests, so it has 0 kinetic energy. Now, we've already defined gravitational potential energy. The highest point is when it has its maximum gravitational potential energy, then things flip around and the energy goes back to kinetic rather than potential. So in that particular case, let me write it down explicitly, but it turns out to be a super easy way to solve problems now using energy rather than force. Either is fine. It's an alternative framework. So this is my thrown ball. Okay. So start off down here. This is y equals 0. I'm going to choose that is my launch point. I start off with some initial speed, call this v1. So since I'm choosing y equals 0 here, and I'm going up to maybe a height y equals h. So as I go up, my change in gravitational potential energy becomes mgh. This thing has a mass m. And of course, down here, my kinetic energy is just a half mv1 squared. Up here, the velocity is 0. So change in kinetic energy as I go up is 0 minus 1/2 mv1 squared. Final kinetic energy minus initial kinetic energy. We claim energy is conserved. Delta U plus delta K equals 0. So delta U plus delta K equals 0 plus mgh minus 1/2 mv1 squared equals 0. M is a constant, get rid of this. This allows me trivially to figure out relationship between height and speed here. Obviously, the acceleration due to gravity is fixed, the half is just a number. So this allows me to get a relationship between the height that this thing is going to go to and the launch speed. So, of course, I can apply this anywhere else in the trajectory. I don't have to be at the extremes, the top and the bottom. I can be anywhere else. In that case, of course, the energy is divided in some way between potential and kinetic. So all it's done for us so far is provide us an alternative framework to learn something about the motion. And again, we could have gotten this from using our equations of motion under constant acceleration, but it's an example of inventing a new framework for us to be able to solve problems. Yes. All right. So, it doesn't seem to have bored us a whole lot yet, but I'm hopefully going to convince you next Tuesday when we work the problem in class that can buy us quite a bit more. But for cases where life's a bit more interesting, where motions might be a lot more difficult to predict or calculate with Newton's law approach, then this new energy framework can be kind of helpful. So let's see. Get rid of this one for a moment. All right. Ball on a string, maybe an example of what we would call a pendulum, at least if it has low amplitude motions. Okay, so I'm going to kind of ask you to talk me through the inverse of what I just talked about with the thrown ball. I'm going to lift up this tennis ball on the string, and I'm going to start it so it's roughly horizontal here. Okay, I'm going to let this thing go. What's going to happen? It's going to swing. Okay, not super exciting, but you guys applaud for anything, so let's give this a go. Okay, here we go. So, okay, it's going to swing back and forwards. Eventually, good job. Eventually it loses energy and its amplitude of swing starts to get less. So that's a departure already from ideal behavior. So the losses of energy, well, drag force in the air, probably some energy loss, kind of friction related in the string, a little bit less hard to describe. Anyway, it's certainly losing energy, so it's not ideal. But you could kind of easily, well, not so easily in that case, actually, but you could figure out the motion using Newton's laws. The reason I say not so easy is if you were to draw a free body diagram for that suspended tennis ball and think about what that force diagram looks like at every different point on the trajectory, well, of course, gravity is acting downwards all the time, but it's acting continually at a different angle to the tension, okay? So that would be not a trivial thing to solve with Newton's laws, because your free body diagram would look different at every point along the motion. You don't have constant forces any longer. All right, so energy maybe is going to provide us a new way to sort of solve problems like that a little bit more easily. But let's make it more interesting, more complicated, where again, the sort of departure from a simple Newtonian force-based analysis is going to give us trouble. So now I've just put a block in the way, there's kind of a pole sticking out here. So this thing can't any longer swing freely backwards and forwards. But we still, in principle, have energy conservation to work with now. So if I launch this thing from horizontal at this point, it's no longer going to be possible for this thing to swing freely back and forwards all the way to the opposite side. But maybe energy conservation will still tell us something about, for example, how high does this ball go when I release this. So let's see. I didn't throw that very well. Try it again. A little better. Still doesn't quite make it all the way up, but look where it goes. Where its height is at the end of the motion. Close, right? Wow. I'm kind of tempted to try stand-up comedy after this. Trust me, I won't. I would not enjoy that. But what you're seeing there, not quite, again, because it's not an ideal system, is that you're seeing that the ball pretty much goes back up to its original height. Okay? Again, energy considerations tell us that if the system doesn't lose any energy, it's not quite true in this case. We know there are places where energy is dissipated. But we got rid of the air and so on and so forth. The ball is going to go back up to its initial height in a rather complicated trajectory. So rather than have to worry about Newton's law of forces, solving Newton's laws for problems like this, we now have a new framework that's going to allow us to work in particular in cases where the forces are changing constantly or we don't get fully understanding what. Okay, that is a good ending point. Let's stop there. Reminder about everything in terms of prep for Thursday. Take advantage of all of the help. And most importantly, if you want a left-handed seat, send me an email in the next 35 minutes. And we'll see you on Thursday at 4. You can figure out, for example, the length of this by using the law of cosine. So, for example, the length of this so the length of the back to the other stuff when we looked at vectors. Again, I'm not going to encourage you to use your cosine or whether it might be useful in general for vector sums. It is mentioned early on in the chapter. We're going to look at this. Take a look back at my notes or the textbook. Just to see if I look it out and see if it makes sense. To be honest, by and large, after that, don't worry about it. I kind of prefer that you're using just the lowest wing or something. Okay, good question. I'm going to erase the chalkboard while I talk. Yes, okay. Go back and waiting just a moment. I'll be right back. Next quick question.
חייב לקצר את החיבור שלי.
איזה חיבור?
סלסה. ומה? למה? למה איך כזה?
צד שלי מחפש.
כן, לא, את השקין שלנו מפה. גם את הבן ממבר צריך לשים. כאן שלחתי אותם. צריך אותה? מי? אז צריכה לצ'נג את the order.
Oh, Lamar, you know the drill, right? You know the drill, right? I'll fill you in before I get
תקצר אותו. מחר. כן. מה, איך אנחנו נעשה? כן. מה זאת אומרת? נכון מדי. גם אני חייב קצת את האור הזה, הוא ארוך. כי מצא לי כל זה, אני חושב מה, זה השיר האחרון. זה הבקעת ביום שלי, תגידי מה את חושבת. זהו, אני מאוד זה משהו אחר להוריד. אז יש מלא ציטוטים כאילו של ה... כן, אני רואה
I thought today was harder than the regular Tuesday. I'm like struggling. I'm very I was talking about
Content related to television.
that was. Did you do all of these? Are these the beautiful faces? That's what I was thinking. Yeah. That was my guess. I know someone. Yeah, it is. There's an actual someone in Bangalore. What did yesterday? You were gonna street code. I mean, let me. It's under like, it might be under the grass, but like, it's like when the bride's pregnant. I hate it when that happens. Like, you think you get it. No, it's there. I think they can. I'm so confused by this whole game. I'm the only one then they won't.
I mean, I bet you do dream, but you probably don't. Did you ever just not dream?
Yeah, that's not the sentence. That's the sentence you might say.
I did go Lab
It's starting to make sense to me. I've heard of this music.